Rendering hair in real-time graphics is notoriously difficult. Individual strands are often thinner than a single screen pixel, so low-sample rasterization creates severe undersampling, aliasing, and noise. Standard denoisers like TAA, DLSS, or FSR struggle because they operate on the final RGB image, where lighting, visibility, and shading are already entangled. Fixing color doesn't fix broken geometry. This research introduces a lightweight, real-time neural pipeline that reconstructs hair G-buffers before deferred shading. The core idea is simple. Coverage and tangent maps are locally correlated and predictable, while position and depth are too sparse to learn directly. The architecture runs in two phases. First, a dual-branch UNet processes noisy coverage and tangent buffers separately, fusing them at the bottleneck with multi-head self-attention to capture long-range strand flow. A parallel hierarchical filtering branch adds a stable low-frequency prior. This spatial pass runs per frame. Next, a compact recurrent CNN handles temporal accumulation, using reprojected history and motion vector differences to suppress flicker and handle disocclusions. But neural predictions alone won't stabilize deferred shading. The pipeline adds an analytic, tangent-guided position completion step. It classifies pixels as valid or missing, inpaints depth, then uses a bidirectional propagation strategy. For missing positions, it traces backward from the nearest valid neighbor aligned with the reconstructed tangent. For valid pixels, it casts forward votes along the tangent direction, accepting only candidates within a 30-degree angular threshold, and resolves conflicts by selecting the frontmost depth. This preserves anisotropic strand structure while maintaining strict geometric consistency. Evaluated across static and dynamic hairstyles, this method consistently outperforms TAA, DLSS4, FSR, and prior neural hair filters. It achieves a 27 to 30 PSNR, slashes perceptual error by over 70%, and runs at just 0.8 milliseconds per frame. By separating geometric reconstruction from shading, it avoids the blurring and energy leakage that plagues RGB space denoisers, especially on highly tangled hair. If you're working in real-time rendering or neural graphics, this G-buffer-first approach is a clean, efficient way to tackle subpixel geometry. The full paper breaks down the training pipeline and architecture, so check it out, and let me know how you'd implement this in your engine.